A very good day to Dr. Amani. We are from Group 1 to present our group project. So in my group, here are my teammates. My name is Michael, and my teammates are Ahmad Shad, Firas, and Isni. Introduction. So, flash distillation is a single-stage separation process used to separate a feed or liquid mixture into separate components. The product upstream of the distillation is vapor product, while the bottom stream of the distillation is liquid product. The liquid component with lower boiling point is more volatile, that will result it to enter the vapor phase, while the liquid component with the higher boiling point it is less volatile, and therefore it will remain as liquid phase. Project goals. In this project, we are given a binary mixture of methyl, ethyl, ketone as component 1 with toluene as component 2. So the project objective is to design a flash for separating the binary mixture given. So for step one will need to determine the initial composition, temperature, and mix and pressure of the feed solution. So in our group, we decide to set the composition of methyl ethyl ketone, the component one as 0.5 mole, while the toluene as component 2 as 0.5 mole. Means the feed solution are in equimolar composition. Next, our initial temperature, meaning the inlet temperature is 95 degrees Celsius, and also the inlet pressure is 100 kilopascal.
So I'm going to continue with the discussion for calculation with the step 2, which is the calculation of saturation pressure for both methyl ethyl ketone and toluene. Here we have labeled that methyl ethyl ketone as the first compound and toluene as the second compound. To find the saturation pressure, we have to use the Antoine equation. Then we have obtained the P saturation for methyl ethyl ketone is 161.6585597, and for toluene is 63.66527906. So we will move to step 3, which is the calculation for bubble pressure and dew pressure. For bubble pressure, we have to use the formula. Obtain the bubble pressure is equals to 112.6619 kilopascal. And for dew pressure, we have to do the same but different formula, which is P dew is equals to 1 over y1 over p1 set plus y2 over p2 set. By doing the same substitution, we can obtain the dew pressure is equals to 91.3533 kilopascal. So the continuation of step 3 is to find the value of K by using the formula Ki is equal to Pi set over P, total P. I means the respective for the respective compound. By doing that, we can get the value for K1, which is for methyl ethyl ketone, is equal to 1.6166, and K2 0.636. Then we're going to move to step 4, is to find the X1 and X2, which is the mole fraction in liquid phase for both methyl ethyl ketone and toluene. We have to use the so by doing the substitution, we can get the value for X1 is equal to 0.3708 and value for X2 is 0.6292. Then we're going to move to step 5, is the calculation of mole fraction in vapor phase, which is Y. The Y1 is for methyl ethyl ketone and Y2 is for toluene. So for that, we have to use the formula K equals to Y over X. We have to use the respective value for each of the compound, which for Y1 we have to use the K1 and X1. So by doing that, we can get the value for Y1 is equal to 0.5994 and Y2 is equal to 0.4006. Then we're going to move to the last last step, which is step 6, which is the calculation of V and L. For V, we have to use the formula. Value for V is equal to 0.5942. To find the L, we have to minus the V with 1, which we have obtained that 0.4058. Okay, that's all for me. Thank you.
Okay, now I will be presenting the PXY diagram. Okay, on the left, the PXY diagram starts from 0 to 1 for x1 and y1. Okay, as we can see, as P decreases, the vapor phase increases while the liquid phase decreases. That's why we can see here on the graph that it from the left to right it slowly increases. Okay, and due to how it flows, we see that the dew point lies on the PY1 curve. Okay, next is the TXY diagram. Okay, opposite to the PXY diagram, the TXY diagram slowly curves down. So from how it flows, we see that as T increases, the vapor increases while the liquid decreases. Okay, and due to this, we can see that the dew point will lie on the TY1 curve. Okay, lastly is the summary diagram. Okay, from the summary diagram, we can see that the feed condition is 50 mole percent of methyl ethyl ketone and 50 mole percent of toluene at 95 degrees Celsius and 100 kPa. It enters the flash column and will exit in two streams. First is the vapor stream and the liquid stream. For the vapor stream, we will see that the methyl ethyl ketone is 59.9410 mole percent, while the toluene is 40.0590 mole percent. For the bottom stream, the liquid stream, we will see that the methyl ethyl ketone will be 37.0788 mole percent, while the toluene is 62.9112%.
So, I will explain the applications of the flash column parts. The flashing system are very common in several industries for the ability to separate vapors from liquids. One of the top industries that using this flashing system is petroleum refining. The amount of components that might be flashed directly depend on either the pressure or temperature or the composition of the stream. It is used through all the common processes of petrol refining, such as crude oil distillation, hydrotreating, reforming, isomerization, alkylation, steam cracking, fluid catalytic cracking, and even caulking. Next, it is one of the most common example of industries that using flashing system, which is petrochemical industry. It is use a lot of light gases for separation processes, mixing, reaction, product generation. For example, the hydrogenation of species, dealkylation, cracking, and also steam reforming. Most of these cases will eventually lead to some gas formation, which must be flushed out of the system.